Welcome to the video lecture series of solid state devices, course code EC301. The chapter is Field Effect Transistor. Myself, Dr. Shunipa Roy, Assistant Professor of Electronics and Communication Engineering Department, Guru Nanak Institute of Technology, Kolkata. This lecture means for Module 4 Field Effect Transistor of Solid State Devices syllabus. This is lecture 10. Module 4 consists of junction field effect transistor, construction, field control action and characteristics, pinch of voltage derivation, numerical problems. The lesson plan is field control action and characteristics, recapitulation, pinch of voltage derivation. So let us describe what are the small signal JFET parameters. So small signal JFET parameters are: number 1, AC drain resistance, that is denoted by small rd. What is AC drain resistance? It is the ratio of change in drain to source voltage to the change in drain current at constant gate voltage. That is AC drain resistance RD equals to del VDS by del ID. That means change in voltage by change in current at constant gate to source voltage. For instance, if a change in drain voltage of 2 volt produces a change in drain current of 0.02 milliampere, then AC drain resistance equals to 2 volt by 0.02 milliampere, that is equals to 100 kilo ohm. So next point is transconductance, GM. What is transconductance? The control that the gate voltage has over the drain current is measured by transconductance. It may also be defined as the ratio of change in drain current to the change in gate to source voltage at constant drain source voltage. So transconductance equals to change in drain current by change in gate to source voltage when VDS is constant. The transconductance of a JFET is usually expressed either in milliampere per volt or micromole. Let us take an example. If a change in gate voltage of 0.1 volt causes a change in drain current of 0.3 milliampere, then transconductance would be 0.3 milliampere by 0.1 volt, that is equals to 3 milliampere per volt. So let us see what is the mathematical expression for GM. We know the Shockley's equation ID or IDS equals to IDS into 1 minus VGS by VP whole square. That is the equation for drain current of a JFET. If we differentiate it in both sides with respect to VGS, we have del ID by del VGS equals to 2 IDSS 1 minus VGS by VP into minus of 1 by VP. So del ID by del VGS, just we have uttered that is GM. So GM equals to minus 2 IDSS by VP into 1 minus VGS by VP. When VGS equals to 0, we may consider that GM equals to GMO. So when VGS equals to 0 in this equation, when VGS equals to 0, this part as a whole 0, this part is 0, that means this total part is as a whole 1. So GM can be replaced by GMO. So GMO equals to minus 2 IDSS by VP. So the final formula is, if we replace this minus 2 IDSS by Vp by GMO, then GM equals to GMO into 1 minus VGS by Vp. So this is the final formula of transconductance. Moving to our next slide. Amplification factor, the third one, the very important factor. It is the ratio of change in drain to source voltage, that is del VDS, to the change in gate source voltage, that is del VGS, at constant drain current, that is amplification factor mu equals to del VDS by del VGS at constant ID amplification. So, for instance, if the amplification factor of a JFET is 50, it means that gate voltage is 50 times as effective as the drain voltage in controlling the drain current. So what are the relations between these three parameters? The relationship among JFET parameters can be established as under. We know mu equals to del VGS by del VGS. Mu is the amplification factor. So output voltage by input voltage is mu, when ID is constant. Now if we multiply it by ID and also subtract it by ID, then mu becomes del VDS by del ID into del ID by del VGS. And we know del VDS by del ID is nothing but RD, and del ID by del VGS is nothing but GM. So mu equals to RD into GM. It is proved. That is amplification factor equals to AC drain resistance into transconductance of the device at that particular temperature. This is the JFET drain characteristics. As the VGS is decreasing from 0 volt, the drain current is also decreasing. So this region is basically cutoff region. This region is breakdown region. This region is ohmic region. And this region is active region or pinch-off region. So the current corresponding to Vp is denoted as IDSS, that is drain to source saturation current. Moving to the next slide. Derivation of pinch-off voltage Vp. Pinch-off voltage, what is that? The pinch-off voltage can be defined as the gate to source voltage to achieve pinch-off condition. The internal pinch-off voltage VPO is the effective PN junction voltage to achieve pinch-off condition. For the simplicity, one-sided N-channel JFET has been considered. Here you can see the maximum channel thickness that has been considered is W for one-sided junction, and the depletion layer width that has been induced is H, is shown here. To find out the pinch-off voltage of JFET, the gate to source voltage should be 0. So VGS equals to 0. For easy approximation, the abrupt junction has been taken and the space charge layer W is given by twice epsilon S VBI minus VGS by E into ND to the power half, where VGS is the gate to source voltage, VBI is the built-in potential barrier, as one-sided abrupt PN junction has been considered here. Epsilon S is the permittivity, ND is the donor atom concentration, E is the electronic charge. For an N-channel JFET, gate to source voltage must be negative to make the P plus N junction reverse biased. When pinch-off voltage is reached, that is when W equals to H, the effective voltage across the junction is VBI minus VGS, which is equivalent to internal pinch-off voltage VPO. So VBI minus VGS in this equation can be replaced by VPO. So the resultant equation becomes H equals to twice epsilon S VPO by END to the power half. So from this equation, we are getting the pinch-off voltage VPO equals to E into H square, that is depletion layer thickness, into ND by twice epsilon S. This is for N-channel JFET. Though the pinch-off voltage that is considered is a positive quantity, still it doesn't mean the actual gate-to-source voltage applied to achieve pinch-off is positive. At that particular instant, VGS can be considered as VP and the equation can be rewritten as VBI minus VP equals to VPO. So VP equals to VBI minus VPO. Here, mind it, VP is nothing but the gate-to-source voltage. So pinch-off voltage is negative quantity for an N-channel JFET. Here we can see that. Similarly, for P-channel JFET, VPO equals to EH square ND by twice epsilon S. The pinch-off voltage for P-channel JFET is a positive quantity. Considering all internal parameter constant, the internal pinch-off voltage for a P-channel JFET can be written as VBI plus VP equals to VPO, or VP equals to VP minus VBI. This is the final formula of VGF for an P-channel JFET. When W equals to H, that means discharge region has covered up the total channel region. So moving to our next slide, there are two types of characteristics of JFET. One is transfer characteristics, which gives relation between ID and VGS. Another one is drain characteristics that gives relation between ID and VGS. And second one is transfer characteristics that gives relation between ID and VGS. So this is the drain characteristics of JFET. So this part OA actually is the characteristic is linear, indicating that for low values of VDS, current varies directly with voltage following Ohm's law. It means that JFET behaves like an ordinary resistor till point A. So now we are concerned about curve AB. In this region, ID increases at inverse square law rate up to point B, which is called pinch-off point. Here we can see that is BP. This progressive fall in the rate of increase of ID is caused by the square law increase in depletion region at each gate up to point P, where the two regions are closest without touching each other. Two depletion regions are closest, but they are not touching each other. And the drain to source voltage VDS corresponding to point B is called pinch-off voltage VPO. But it is essential to remember that pinch-off doesn't mean current off. Rather, current is maximum at this point. That means the channel is saturated by the drain current. If we increase the drain to source voltage, the drain current will not increase. Now, this BC region is called pinch-off region. So, it is also known as saturation region or amplifier region. Hence, JFET operates as a constant current device here because ID is relatively independent of VDS. So, it is due to the fact that as VDS increases, channel resistance also increases proportionally, thereby keeping ID constant to IDSS. It should also be noted here that the reverse bias required by the gate channel junction is supplied entirely by the VDS alone. There is no external bias applied at VGS. So drain current in this region is given by the Shockley's equation. ID equals to IDSS 1 minus VGS by VP whole square. This can be written as ID equals to IDSS 1 minus VGS by VGS of whole square, where IDSS is the drain current. When VGS equals to 0, VGS of is defined as minus VP, that is gate to source voltage that just pinches off the channel. The pinch of voltage VP here is a positive quantity because it was introduced through VDS set. Now, breakdown region. If VDS is increased beyond its value corresponding to point C, called this point actually called avalanche breakdown point, JFET enters the breakdown region where ID increases to an excessively. This happens because the reverse biased gate channel PN junction undergoes avalanche breakdown when even small changes in VDS produces very large changes in ID. It is interesting to note that increasing value of VDS make a JFET behaves like a resistor in ohmic region, then as a constant current source in pinch-off region, and finally as a constant voltage source in the breakdown region. Because if you keep on increasing the voltage, it is not increasing the current. So it behaves like a constant voltage source in the breakdown region, constant current source in the pinch-off region, and a normal resistor in a ohmic region. Isn't it interesting? So moving to our next slide, this is the JFET transfer characteristics. So why this is called transfer characteristics? See, in x-axis we have taken VGS, that is the input gate to source voltage, but in y-axis we have taken ID, that is output drain current. As this characteristics is the amalgamation of input voltage and output current, that's why this is called transfer characteristics. So VGS should be negative always. So here we can see VGS is negative, -2, -4, -6. And if VGS is 0, current is maximum, that is IDSS saturation value, ID drain to source saturation current, and we keep on increasing or decreasing the gate to source voltage. Current is gradually decreasing here, and at points VP, that is pinch-off voltage, we find that the current is 0. That means current is, the device is cut off. No more current is flowing through the device when VGS equals to minus VP. This is called transfer characteristics of JFET. So moving to our next slide. So to construct the transfer characteristics or transconductance characteristics, when VGS equals to 0, ID equals to IDSS, and when ID equals to 0, VGS equals to minus VP. So transfer characteristics like this follow Shockley's equation, and if we rewrite this formula, we can also write it as VGS equals to VGS of 1 minus root over of ID by IDSS. Moving to the next slide. This is the amalgamation of drain characteristics and transfer characteristics. If you find that the current is same, the magnitude of current is same for drain characteristics and also for transfer characteristics, but the voltage is varying. Say when voltage is 5 volt, VDS when 5 volt, then say 0.5 milliampere current is flowing through the channel. Similarly, when VGS equals to -3 volt, 0.5 milliampere current is flowing through the channel. So when VGS equals to minus 3 volt and VDS equals to 5 volt. Similarly, when VGS equals to minus 2 volt and VDS equals to 5 volt, same 2 milliampere current is flowing. Similarly, VDS equals to 5 volt, VGS equals to minus 1 volt, 4.5 milliampere current is flowing. If we keep on increasing VDS, current is not increasing in the drain characteristics. But if we keep on increasing VGS, magnitude is increasing, but the actual value is decreasing. The current is gradually decreasing in the transfer characteristics curve. So moving to the next slide. What is the process of plotting this transfer characteristics curve? Plot a point that corresponds to value of VGS of here. Plot a point that corresponds to a value of IDSS, this point. Select 3 or more values of VGS between 0 and VGS off. That is minus 2, minus 3, minus 4. Determine the corresponding value of ID from Shockley's equation. Now plot these points and connect it, you will get the transfer characteristics curve. Now, our next concern is JFET configuration. CS, CD, CG. What is CS, CD, CG? CS is common source configuration, CG is common gate configuration, and CD is common drain configuration. So let us see what is this. Like bipolar junction transistor, common source configuration is shown here. Source is common to input as well as output. This left portion corresponds to input portion. The right portion corresponds to output portion. So, common source configuration is an analogous to the common emitter configuration in the bipolar junction transistor. In this configuration, input voltage is applied to the gate terminal, and the output we get is from the drain terminal. Here you can see this is drain terminal and input we are applying at gate terminal. This mode of operation comes with amplified voltage and high impedance. Hence, it is mostly used in high audio frequency amplifier. As this is an amplifying circuit, it allows the output to be delivered 180 degree out of phase from its input. So, this slide depicts the common gate configuration of JFET, analogous to the common base configuration of bipolar junction transistor. In this configuration, input voltage is applied to the source terminal and output appears at the drain terminal, while gate is connected to ground. Impedance will be low as compared to the common source configuration. This circuit mostly used in high frequency and impedance matching device. Here, output signal is in phase with the input signal. So, our next matter of concern is common drain configuration. Common drain configuration is analogous to the common collector configuration of bipolar junction transistor. In this configuration, input voltage is applied to the gate terminal and output signal is connected from the source. It is important to note that there is no signal applied to the drain terminal. VDD simply depicts the bias voltage. Similar to common gate configuration, here output signal is in phase with the input signal. So this is the comparison. Please have a look. This is showing voltage gain. This is showing current gain. This is showing power gain. Then input output phase relationship, input resistance, output resistance and application. This is a quick review. So moving to our next slide. Now small signal model of JFET. For small signal model, we don't have to consider the capacitance effect because capacitor is open when the frequency is low. So nonlinear devices can be reduced to a circuit composed of linear elements. That means the nonlinear characteristics of a device is represented by hypothetical linear circuit of ideal circuit element which would have the same characteristics as the nonlinear device. This actually eliminates the difficulty of analyzing nonlinear circuits and reduces the nonlinear problem to a set of linear problems which can be easily solved by the circuit theorem, that is Thevenin's theorem, Norton's theorem, etc. So here we can see this is the gate current Ig, this is the gate to source voltage VGS when small signal is applied. This is the dependent current source. This is the output impedance RO and this is the drain resistance, drain current ID, and this is the drain to source voltage VDS. These dependent voltages actually depend on the voltage VGS, input voltage, gate to source voltage. That's why this is represented as GM VGS. This is source terminal, this is gate terminal, and this is drain terminal. The input is open, the input impedance is very, very high, infinite. That's why the input kept open. So here we can do some practical problems. So go through problem 1 first. Figure shows the transfer characteristic curve of JFET. Write the equation for drain current. Here we can see IDSS is 12 milliampere, VGS off is minus 5 volt. So we can write the formula easily, that is ID. This is the Shockley's equation. Put the values here. ID equals to 12 into 1 plus VGS 5 whole square. This minus and this minus 5 comes to plus 5. This is the answer. This is another example. A JFET has the following parameter: IDSS 32 milliampere, VGS of minus 8 volt, VGS minus 4 volt. So find the value of drain current. Put the values here, you will find 6.12 milliampere. Here is another example. IDS is given, VP given, transconductance given, VGS given. Sorry, we have to find out transconductance. So IDS given, VDS given. This is the formula of transconductance. Now we are getting GM equals to 0.5 milliampere per volt. This is how to draw the transfer characteristics curve. When IDS is 12 milliampere, VGS of equals to minus 6. So VGS when 0, then ID equals to IDSS. So VGS is when minus 3 VP, then ID equals to IDSS by 2. Put all these values in Shockley's equation, you will get the answer. When VGS equals to minus 0.5 VP, then ID equals to IDSS by 4. So minus VP, when VGS equals to minus VP, we know ID equals to 0. So next exercise is put ID equals to IDSS and VGS equals to VP. Then put intermediate values and intermediate value corresponding current. Join these points, you will get the transfer characteristics curve easily. This is the answer. So this is the reading material of this section. If there is any question, please feel free to ask me. This email ID. Thank you for paying attention.